All right, welcome back. So we'll be still talking about interference today. Um, so um, remember when we talk about the superposition of waves, if two waves they meet at a certain location together, so the wave function add up. Okay. So then if you have y1 as a sine kx minus omega t, and then y2 as a sine kx minus omega t, and then with a different phase shift, right? So if these two waves, they have slightly different in phase when they interact with each other, then depending on what this difference in phase you would have, so the result of these two sine function add up, right? It's according to one of the trigonometry identities, specific relate to half angles. So then it's equal to twice of a cosine omega divided by 2 sine of kx minus omega t plus omega divided by 2, or delta. Sorry, this is delta, not omega. Lowercase of delta. So then you get a new amplitude and with a sine function. Okay. So depends on the phase difference of the delta. If delta is equal to 0 or multiples of 2 pi's, then the two waves will add up. Okay, so the amplitude doubles in that sense. If the two have the phase difference of equal to pi or 180 degrees, then the two waves actually cancel out completely. Then you get destructive interference. Okay, in the case of the two add up, we call it constructive interference. Also, there's phase change. If we have wave that goes from one medium into the second medium as the refraction happens, so in the refracted wave that comes back, right? So if you go into if your wave goes from a thinner medium enters a thicker medium, then part of the wave will transmit into the second medium, the thicker one, and the other part of it will be reflected back. So if that's the case, going from thinner to thicker medium, the reflected wave will have a phase shift of 180 degrees, so it flipped completely. On the other hand, if the wave propagates from a thicker medium into a thinner medium, okay, so again, part of it will be transmitted into the second medium, part of it will be reflected. In this case, for the reflected ray, or the wave in this case does not have a phase change. Okay, so it depends on the scenario if the two waves has initial phase difference or if they reflect from one medium to a second medium, depending on the medium, right? Which one has the thinner or thicker in that sense, material. So for the thinner one, it has less index of refraction. For the thicker one, it has larger index of refraction. Okay. So then let's take a look on this. So for light, which is a wave that has, so let me see if I can get this header out of the way. Okay, so light has a wavelength of 500 nanometers instant, normally on a film of water 1.00 micrometer thick. What's the wavelength of the light in the water? And then how many wavelengths are contained in the distance 2t, where t is the thickness of the water. Okay, the thin film has air on both sides. What's the phase difference between the wave reflect from the front surface and the wave reflect from back surface in the region where the two reflected waves superpose? Okay. So let's take a look on this example and then see what we learned just a couple minutes ago, how those two scenarios apply here. Okay. So let's list thin film of water, 1 micron, 1 micrometer. Okay. So this thickness is 1 micrometer. T equals to 1.00 micrometer. All right, wavelength lambda equals 500 nanometer. Okay, so it's asking you what's the wavelength in the water. We learned in the previous lecture, so for wave to go from vacuum or air, so vacuum and air, they are about the same. Okay, so that's the wavelength in air or in vacuum, 500 nanometer. When it enters a medium, okay, of index refraction, so then the wavelength decreases by the factor of the index refraction. Okay, so in this case, so the wavelength of the light in the water now it becomes 500 nanometer divided by index refraction of the water, which is 1.33. Okay, so that's a constant number, 375 nanometers. Okay, so that gives you that. Okay, so again, for wavelengths, it changes when it enters a medium of index refraction by a factor, reduces by a factor of n for index refraction. Okay, so now let's take a look on B. How many wavelengths are contained in the distance of 2t? Okay, so then you do 2t, right, divided by the wavelength. So remember, because 2t is the thickness of this guy, of the thin film, so then you're talking about, this is what it means. So it says you can see a light goes here, right? Get reflected partially. So reflected ray. So maybe imagine this is a certain angle, right? Reflected ray on the first one. Now part of it will enter the median and then get refracted on the second here. Okay. So there's a wave number one, refracted wave, there's a refracted wave number two. Okay, so these two, for these two, if they go into the observer's eye, somewhere here, right? So then for the path difference of these two, wave one and wave two, refracted wave one and wave two, the path difference is by this 2t. Okay, so think about this as the twice of the thickness of this. Okay, so 2t. So that's where this 2t comes in play. Okay, so 2t over lambda then is equal to 2 times 1.00 times 10 to the minus 6 nanometer micrometer divided by 375 nano 10 to the minus 9 meters. Okay, so that gives you 5.33. Okay, of wavelengths are contained in that 2 times of the thickness. Okay, for C, it's asking you the film has air on both sides. What's the phase difference between the wave reflected from the front surface and the wave reflected from the back surface? Okay. So we are talking about phase difference. Okay. So remember, in this case, we have to analyze the scenario, right? If you're going, so this is air. It's air here. Let's call it N1, and then this is water, NW, or NA, air. So 1.00. This is 1.33 air again on the other side of the film. So the first wave, or for the wave strike on the surface on one side, right? So that's the first refracted ray. So you go from, as you are going from the thinner median, 1.00, to a thicker median, right? The refracted ray here now would have a phase shift of pi. So for this guy, you receive pi phase difference, or 180 degrees, okay? Now part of it enters here. Now it's traveling in the water, and it then hits on the second surface. So then there will be like refracted ray, okay, of ray 2, and then transmit ray goes in there. So for this second one, because it's going from water to air, so the refracted ray now do not have, so no phase shift, okay? So 0 phase shift or 2 pi, or we should just say 0. There's no phase shift, okay? So then for these two, then you'll get the difference, right? So for this guy, the second one remains the same. The first one has the phase shift of pi. So then the phase difference between the two refracted ray should be having a pi or 180 degrees of phase shift. Okay, so in that sense. All right. So then as a result, so this is a kind of extension on the problem. It's not asked by a problem, but extension on that. So as a result, for these two waves, refracted waves to reach in the eye of the observer. So this is a path difference, okay? Path difference. And then this is due to phase shift, okay, of the refracted rays. Right. So these two then would add up. Okay. For this guy, in terms of path difference result in the phase shift delta, again, so translated to delta, then it's 5.33 times 2 pi, okay, for that guy. And then this one will be added up to that guy, okay, so the total delta phase difference due to the path difference and then the phase shift should be the 5.33 times 2 pi and plus pi. That will be the total phase difference, okay? All right. So that's kind of foundation for the main topics of today. Let's go to the PowerPoint slide. So thin film interference, right? So when you blowing soapy water bubbles into air, you're likely to see bright fringes, like maybe purple, blue, or sometimes maybe red in that sense. So that's then due to the fact that the light hits on the surface of the bubble, get reflected one time, and then the other part enters the bubble and then get reflected a second time on the back surface. And those two reflected rays goes into your eye. Now they have phase difference due to first path difference and then the second phase shift of the refract rays. Okay, so depending on scenarios, then based on the phase difference delta, if delta is 2 pi's of the multiple integer number multiple of 2 pi's, then you get construct interference. And then if the delta is equal to the just odd multiples of pi, then you get kind of distract interference. Okay, so it depends. And then there are two scenarios, right? So for this is what you have for the path difference, result in the path difference. Okay, and then for the phase shift depends on. So for this example, N1, N2, and N3, right? So in the previous case, we see N1 and N3 are the same. So then you get the phase difference, okay? But if you have N1 is less than N2, but N2 is less than N3, so then the first ray, refract ray, will have the phase change of pi or 180 degree, right? For the second refract ray, it will also have the phase shift of pi or 182 degrees. So then these two will cancel, okay? So for the scenario N1 less than N2 less than N3, then you only have phase difference due to path difference, okay? For the N1 minus less than N2, but N2 greater than N3, then you don't have the phase difference, okay? Or you do have a phase difference because there's a difference in the, there's no phase change in ray 2, only on ray 1. So then you add pi to the total phase difference, okay? So then as a result, so then the total phase difference due to path difference for the first part, okay? And then this is for the phase change. If N2 is greater than N1, N3, okay? And then for the other case, if both rays both have the phase change, then the phase change cancels. So then you don't have a pi added to, okay? So then you get this. Or in terms of the index of refraction and then the wavelength in the air or in vacuum, you get this expression, okay? So this is lambda n, which is basically lambda divided by n. So lambda sub n is the wavelength in the median, lambda is the wavelength in vacuum, okay? All right. So you can see interference fringes on the soapy water bubbles, like it's showing here. You can also see if you have the two glass slide, okay? So if you make the two has a small gap, you also be able to see the fringes, interference fringes. So that happens when the light hits on the first surface, right? And then get refracted. Now, reflected for ray 1, this case, this is ray 1. And the refracted ray hits on the surface of the second slide, get refracted. So this is refract 2, okay? So there's a path difference between these two for this part and that part. And then there's a might also be in this case. So the first ray will not have the phase change, but the second one will have the phase change. Okay, so there's also phase difference due to phase change. So then when those two arrive at your eye, you'll see interference patterns. So depending on the thickness and the wavelength, and then you can tell which one has the construct interference as shown here. Okay, so that's the ones you'll be able to see. Also, if you look at this glass like kind of lid, curved lid, so then similar to the thin film, so light hits on the surface, get reflected one time, and then the other part get into the glass, hit on the back side of the glass, and then get reflected. So for those two, again, you look at the path difference plus the potential phase change of one of the rays, then the total phase difference can be determined, and then you can tell which light will be constructed interfere, okay, due to that, depending on the thickness and also the wavelength. Let's take a look on the example here. So it says a film of oil that has an index of refraction 1.45 rests on an optically flat piece of glass with an index refraction of 1.60. Okay, so let's maybe sketch this one first before we move on to the switch our camera. Okay, so let's see it here. So it says a thin film of oil. Okay, so this is a thin film of oil, and it rests on the piece of glass. Okay, so this is glass. So we have air, oil, and glass. Air will be having index reference 1, right? Oil, it says 1.45, glass, it says 1.60. So N1, N2, and the N3, okay? So and this is the case N1 less than N2 less than N3, okay? So it says when illuminated with white light at normal instance, light on wavelength 690 and 460 is predominant in the reduced reflect ray. Determine the thickness of the oil film, okay? So let's see. So normal instance, okay? So normal instance goes in here, and so get reflected. I'm going to just shift on the side so we can see the ray, reflect ray. So reflect ray number 1. Okay, the other part will enter and then get reflected. So I'm going to shift it over here so we can see the reflect ray emerging on that. So the ray 1 and ray 2. Okay, so delta due to path difference should be 2t over lambda m. Okay, the thickness. So the t is the thickness of this oil film. Okay, times 2 pi. Okay, so this is due to the path difference. Okay, path difference. Now plus, let's see if these two rays have, if just one of them have their phase shift, right? So from thinner N1 to N2, so then this guy, yes, has a pi shift, okay? For this one, it's from N2 1.45 to 1.6. So it also will have a pi shift, okay? So then the 2 pi and pi actually they cancel, okay? So will be then as a result will be 0, okay? So you see two predominant light So that means those two has construct interference. So these then should add up to be 2 times m times pi, or n times 2 pi, or if you want, you can use m. So maybe let's stick with m, because that's the notation we use a few slides back. Okay. So then, okay, so this then will be the equation you have you working at. Okay, so 2t divided by lambda sub n. So let's talk about that. Lambda sub n is equal to lambda over n. Okay, so then we can do substitution there. So then on the top here, you would have 2nt over lambda. Okay, times 2 pi equals to m times 2 pi. Okay, so 2 pi will cancel. So then you would have 2nt over lambda equal to m for the predominant light. Or the light has constructed interference. Okay. All right. So it says two lights have that, right? So the first one will be the 690. So you can set up 2 times n. So n will be in the median. In this case, it will be n2. Okay, so let's just write that down. 2 times n2 here. 2 times 1.45 times t over 690 nanometer. Okay, nanometers. So let's say 10 to the minus 9. Okay, meters is equal to m. Okay, so this is m. This is the order of the interference. Okay, nth order, m's order, and this is the units. So let's just leave out the unit form right now because it could be confusing from time to time. All right, now for the other one, you can also write it out. 2 times 1.45 over t divided by 460 nano, right? 10 to the minus 9. So if this guy has m numbers of order, the next one here, you see the top denominators being the same, numerator is smaller, so then you should get a larger number here instead of m, right? So then you probably get the next orders of interference, so m plus 1, okay? So that's what these two tells you. All right, so in this case, you can see you have two equations. You have two unknowns of m and t, okay? So you can solve for the m and t at the same time. So you can do substitution, right? So this one goes down, and then you can do the substitution. So you guys should be able to do this. So I'm calling this one, this two, okay? So there's different ways of doing this, but I would like to do this one, like doing equation 1 over equation 2. So that means this side over this side, right? So then 2nt will just cancel. Numerator, denominator stays there, but denominator on the denominator will flip. Okay, so then you get 460 over 690 equals m over m plus 1. Okay, so 460 and 680, they have common factor of 230. So 2 and then 3 at the bottom. So 2 over 3 equal to m over m plus 1. So you can easily see that m is equal to 2. Okay, so m equal to 2, m goes back there. You can solve for your t. So it turns out t to be just equal to 467 nanometer. Okay, so that's your thickness. Okay, so this is how you solve for a thin film interference problem, where you analyze the scenario, right? Depending on N1, N2, and N3 values, you might have a phase difference due to phase shift, right? Or not. If the two both have that, then they cancel. If just one of them has the phase shift, then you end up with pi instead of 0 here, okay? This is path difference. Okay, you write it out, equal to 2 times m pi if it's referring to predominant light. Okay, so then you get this equation. Now apply it to the wavelengths given. Okay, so if you are given just one wavelength, you apply that one time. If you're given two of them, apply them twice. Okay, so in that scenario, and then start from that point on, you should be able to solve the problem. Okay, so that will be it for today's class. And this is the last of the physics 2. So I will see you guys in the class. Bye.